You're at Immutability, or Putting the Dream Machine to Work. You probably came in here expecting a talk called UI, the Functional Final Frontier. It's more or less the same talk. I've just evolved my, my talk idea since the time I pitched it to QCon many months ago. So you are in the right place if that's the talk you were looking for. So yeah, so I want to talk about the Dream Machine today. I want to talk about immutability and how it can help us build sort of simpler user interfaces, or better user interfaces, really. So I've been a JavaScript developer doing front-end work for about 8 years. I was at the New York Times for 4. I recently left about a month and a week ago. I now work for Cognitect. Cognitect is a consultancy and a database company. I think at Cognitect we sort of believe that a lot of software systems are far too complex, and that there's a lot of incidental complexity, and that you can build simpler systems, the same type of systems that we've always been building, but we can build them simpler. And that's really what my talk is really about. I'm not going to show you user interfaces that you've never seen before, but I'm going to show you how you can solve problems that you would think, that sounds really hard. And I can show you that, no, that was incidental complexity. And we can do what look like hard problems. We can make them easy problems. So one thing that we believe at Cognitect is that one way to achieve simplicity is by embracing immutability. Cognitect stewards the Clojure programming language, which is a sort of functional programming language, as well as ClojureScript. I'm the lead maintainer of ClojureScript. And we also build a database called Datomic, which is an immutable database. It's an immutable relational database, which is very cool. You should check it out. I'm actually not going to talk about these things that much today. The thing I really want to talk about is the Dream Machine. If you've never read this book and you have anything to do with user interfaces or interactive computing, this should be at the top of your Amazon list of next things to read. I picked this up because it was recommended by Alan Kay. It is a history of how interactive computing sort of came to be, and it's sort of a history around JCR Licklider, who, because of his work through ARPA and his funding, we have interactive computing. He was a psychologist who became involved in the computing culture. And so a lot of people back then were like, computers are only going to be about building bombs. It's only for scientists. It's only for these extremely wealthy, large corporations. There is no future in personal or interactive computing. And he actually, JCR Licklider, his first success story was building the first interactive missile tracking system when we were in the midst of the Cold War. And so his insight into human psychology and human factors allowed that to be a success. And he was, for 4 or 5 years in the 60s, he led ARPA. The mother of all demos, Douglas Engelbart's group, he funded them. He's the one that directed funds so that the mother of all demos could happen. So behind the scenes, he sort of like created a culture in which interactive computing, or experimentation around interactive computing, could flourish. It's funny, he's very famous for a book called The Man-Computer Symbiosis. This was written in 1960. It's a very highly cited paper. So he was sort of looking into the future. What will it be like when computers are more interactive and human sort of cognition and capability is augmented by interactive computing? And it's funny, he sort of lays out all the things that will be necessary for interactive computing to succeed. And something that he says, he basically predicted my talk. Like this 54 years ago, he predicted almost everything I'm going to tell you today. And he has this really great little point. He says, the tree memory scheme is inefficient for small memories, but it becomes increasingly efficient in using available storage as memory size increases. The attractive features of this scheme are these. One, the retrieval process is extremely simple. Given the first argument, enter the standard initial register with the first character, pick up the address of the second, then go to the second register and pick up the address of the third, etc. If two arguments have this same initial character in common, they use the same storage space for those characters. We're going to be talking a lot about trees. This is a photo of some people that he helped fund. The second from the left is John McCarthy, the inventor of Lisp. He also invented functional programming, programming with recursive functions. He invented garbage collection, invented interpreters, dynamic programming languages, effectively, anything that you do, if you're in this sort of like the programming space, especially if you use dynamic languages, but even if you don't, because even static languages are becoming more interactive, you can thank him. He was a mathematician, and he was very disgusted with the fact that programming itself was not an interactive process. He invented the REPL. It was his idea that, no, we don't type something into a card and send it in and then wait 2 days to get the result and then discover there's a bug. I should be able to sit down at a computer, get a prompt, type it in, and get a response. So it was his radical idea that even the act of programming itself should be an iterative interactive process. To his right is Ed Fredkin. He invented the tree, the data structure that we're going to talk about. He was a college dropout. He went to Caltech. He dropped out, became a fighter pilot, and turned, with no formal education in computer science, was one of the truly great hackers. And he was sort of an important person in the sort of hacking these initial interactive systems where it was like, how are we going to make anything interactive work with such crappy hardware? And he worked a lot of magic. He invented the tree. Okay, so Licklider's group also funded this guy. ARPA did. I mean, Licklider, I believe, had left at this point, but he had put the culture in place such that Xerox PARC and Alan Kay's team could get the funding to develop the Alto. So Alan Kay deeply understood John McCarthy's ideas about that programming itself should be an interactive activity. By sort of internalizing these ideas, he invented the modern UI as well as the modern form of object-oriented programming. Pretty awesome stuff. So if you so he was really interested in education. This is the very lucky kids playing around with an Alto, learning small talk. I think they're 7th and 8th grade, right? Which is wild. They were experiencing the future long before many of us did. What's awesome about this story and small talk is that this is an article by Marion Goldine, who is 11 or 12, and she's describing her experience doing small talk programming. This is in 1973. Marion Goldine is now a very well-respected UI engineer at Apple. So it was her experience on a small talk machine that sort of defined, the rest of her career. So interactive computing is very important. Okay, so if you open up a Smalltalk image today, you can download, there's an open source one called Squeak, download it, fire it up, you look at the GUI, open up a system browser. The system browser shows you every aspect of the running system. You would encounter something very familiar to a contemporary UI programmer. You would encounter these classes. There'd be models, there'd be views, and there'd be controllers. That was invented at Xerox PARC in 1979, 35 years ago, or no, 45 years ago, no, 35 years ago. So it was first formulated by Trygve Reinskog and Adele Goldberg, and it's cast an extremely long shadow, right? Those ideas are still prevalent. People are still building MVC systems. In fact, it was hilarious to watch the JavaScript community in the early days reject MVC only to take an entire decade to come back to it. So I think MVC is fine at a very abstract level. It is a sound separation of concerns. The user has some domain that they care about. That's the model. They have some views. They want to visualize that domain. And then the programmer has to write a controller to sort of keep these things in sync. However, I'm going to argue, my controversial statement today, is implementations leave a lot to be desired. For the past 35 years, we've erected our MVC systems on top of stateful objects. Stateful models, stateful views, stateful controllers. And I want to demonstrate that you can have everything that you like about MVC, and at every level of your system, you can remove statefulness. And lots of interesting things happen when you do that. Okay, and so how are we going to do that? We're going to do that with Licklider's sort of premonition that trees might be important in interactive computing. So I'm just going to use some slides. I'm going to sort of show a data structure which you guys probably aren't familiar with. Even if you like functional programming, you've probably not heard this description of persistent data structures that are implemented via trees. So I'm going to use some slides by Zach Allen. He's a facilitator at Hacker School, which is a really awesome sort of writers camp for coders. It's 3 months long. And he put together these slides for Strange Loop last year, I think. And I'm just going to reuse them. They're just too good. So regardless of whether you like functional programming or not, or you're an object-oriented programmer, it's completely irrelevant. All the ideas I'm going to talk about work in an object-oriented context. But in order to understand where these data structures came from and why people want them, we do have to at least understand the perspective that functional programmers have. Functional programmers like immutable values. They don't like mutable objects. And this is because they want to program with values. So change returns a new value. It leaves the old one unmodified. Now, if you do JavaScript, you get this when you add numbers together, you concatenate strings, right? Strings are not mutable in JavaScript. Numbers are not mutable in most languages. You can't change one. And in fact, this gives you a great amount of reasoning power. So functional programmers said, why is that restricted to these just strings and numbers? What if our collections had the exact same properties that numbers have? We treat collections as values. And so functional programmers sort of really ran with that idea. Can we have the same reasoning power over collections that we have over things like numbers? So they invented this thing called persistent data structures. When they say persistent, they don't mean persistent on disk. They just mean that getting an updated value of a collection doesn't destroy the previous value. And they're fast. And this is a very recent development. There is a book called Purely Functional Data Structures by Chris Okazaki, which was written in 1997, which is cool for paper complexity. It's a paper complexity text. It wasn't until Phil Bagwell at EPFL, which is the home of Scala, he came up with this thing called the hash array map trie, that it was possible to get something that was much closer to the performance of truly mutable data structures, where the gap is actually quite small. It's not just good on paper. The actual performance on modern hardware is very good. So persistent data structure might sound, wow, that sounds crazy. Do I need a PhD in computer science to understand this? You do not. If you understand linked lists, this is like one of the first things every CS person learns. If you understand linked lists, you can understand how persistent data structures work. So I have a list here, and imagine I stored it in a variable x, and it has 4 things in it or whatever. And then I cons. I have a new head, and then I make that other list the tail. And now what's nice about this is I have 2 distinct values that share more than 50% of their memory. Right? More than 50% of their contents are shared here. You can imagine I get the tail of x, and then I cons a z onto it, right? And now and store that in a variable. And now I have 3 distinct values, all of which share more than 50% of their memory. So this is the idea. The big idea behind persistent data structures is structural sharing. And the huge benefits fall out of this. This is also what Licklider was talking about in 1960, sharing memory. So by sharing structure, we get space efficiency, which is obvious from the previous diagram, but we actually also get computational efficiency. By sharing structure, we can actually avoid copying. So if you traditionally, with immutable data structures, people do this thing, copy on write, and copy on write works great when your data set is really small. When it's more than like a couple hundred things, you start losing. So Phil invented this thing called the array map tree and the hash array map tree. And Rich Hickey came along and said, that's an awesome mutable data structure. If I tweak that tree just a little bit, I can get a functional thing out of it. So Rich Hickey invented the Bitmapped vector tree, which is a very specific variant of the hash array map tree. Data lives in the leaves. It's basically an array of arrays, and don't worry if this sounds all confusing because we have some very pretty graphics coming up. It's a prefix tree used for lookup, and it's a bitwise prefix tree. And this is cool because this is the type of thing that many compilers optimize, including the modern sort of family of highly optimized JavaScript engines. So persistent vector is the name. It's the sort of the name we give the bitmapped vector tree. And so it works by, here's the root, and we pick some length. All of the nodes must be arrays, and they must all have the same size. So let's pick an arbitrary size 4. So we have the root. And then every element of that array points to an array of the same dimension. And each of those point to another array of the same dimension. And finally, we get to the leaf nodes, which are arrays of the same dimension that actually contain values. And then you're like, okay, but how do I get something in there? How do I get something out of that? So I want to get item number 106. right? I want to get item number 106. So item 106, there's a very convenient thing here. Item 106 actually has a binary representation, right? And we can actually use that as the prefix to find out where that thing lives. So what do? We mask off the first 2 bits of the number 106. And that tells us we have to go down to index 1, right, from the root. Now we have to go down index 2 from that level. Again, index 2 from that level. We're out of bits to mask, and we know we have to look at index 2, and there's our value, 106. So to get to this required a couple of bit operations and a couple of array accesses. This is the type of thing that modern JavaScript engines generate x86 assembly for. So this is not going to be slow. Okay, what about updating? So how much do we have to pay for updating? So if you want to update something, we don't have to update everything. We just have to update the path that changed. So we have to clone the root. We have to clone the next array on the path to the value we want to update. Again, clone that one, and then clone the last one, and we replace that value. We mutate it, right? And so notice that all the other array nodes that were not involved in that path, they don't change. They don't change. Okay, so you're probably thinking, well, length 4 vectors. Well, what if we play around with that? After sort of lots of empirical evidence on modern hardware, Scala has tested this, Haskell's tested this to some degree, Clojure's definitely tested this. 32 is a very good size because of cache lines for these persistent data structures. It's a good size also for the cost to update and the cost for lookups. Just to give you a sense of how optimal that 32 is as a branching factor, if you had a data structure, persistent vectors, 7 levels deep, only 7 levels, right? That's 32 to the 7th power. That's 34 billion elements, right? On a 64-bit OS, even if this was a regular JavaScript array, flat, not a persistent vector, if it had this many elements and you had object references, so that means you had 64-bit pointers in each slot, that's 256 gigabytes of RAM. Nobody in here in this room has a laptop with that much RAM, right? The cost of updating this data structure, if we could possibly fit on our laptop as a persistent vector, you would have to update only 7 arrays. To get to any element in this structure, you'd have to do at most 7 array accesses and 7 bit operations. So very good. So this is definitely proves Licklider's point. Yes, it might be efficient for small data, but when your data starts getting huge, you absolutely cannot beat this data structure. So let's see how much it actually costs on a modern JavaScript engine. So I've talked a lot, but I haven't shown any numbers. So here what we're going to do, I'm going to show you the cost to build a persistent vector using a recent build of V8. V8 is the engine in Google Chrome. And we're going to compare building a mutable array, and we're going to compare building an immutable vector, a truly immutable vector. And let's see what the cost is. So that's not bad. That should be surprising, right? So to build a million length array where we have just a million numbers in it takes about 85 milliseconds on V8, and it takes about 300 milliseconds using the immutable thing. So this is not an order of magnitude difference. It's about 3.5 times slower, right? So obviously it's fast enough for lots of applications. Many applications is fast enough. But of course, in the Clojure world, we've thought about this a lot. And sometimes you do want to build collections more efficiently. So we actually have a really cool thing called transients. So in the JavaScript world, there's a thing called object freeze, where you can take an object and make it immutable. So we have that because, well, number one, all our stuff is immutable. We have a nice sort of opposite operation saying, I have an immutable value. Give me a mutable version of it temporarily so I can build it very quickly and then convert it back to a persistent thing. And so these are both in Clojure script and Clojure O1 operations. So I want to show you how fast it is to build a transient vector. Okay. So this is comparing building an array with 1 million elements and then building a transient value, a transient vector, and then making it immutable right at the very end. So we build it up to 1 million and we're going to make it immutable. And what's the cost? So it's faster. Transient vectors are faster. It's faster to build transient vectors than it is to build mutable arrays in ClojureScript on modern JavaScript engines. Just to show you I'm not totally pulling your leg, so this is JavaScript core. This is Apple's JavaScript engine. So we're not talking, there's hardly any difference, right? You're not paying for anything here. It's almost 1-to-1 to build transient vectors. Okay, so this is awesome. So thank you, all these crazy people that have been working on optimizing dynamic languages so that we could show cool demos like that. So this is definitely a result of work on self and these optimizing Smalltalk implementations in the 80s and 90s. Very cool. It's also a result of the fact that JavaScript is so ubiquitous and there's such an arms race around making JavaScript fast. I got particularly excited about WebKit announced this thing called the FTL JIT, which is a 4th tier. So their 4th tier is going to absolutely love the type of stuff that we do. We do very low-level stuff in our persistent data structures. Anything to make that faster, it's good for us. It's also pretty cool. I was at JSConf in Florida like a couple weeks ago, and Nick Bray from Google was talking about something totally crazy. Shared memory parallelism in the browser. And he actually showed a demo on stage where you could actually have threads and locks in Chromium. And that sounds like craziness, right? It is craziness. I wouldn't want to do that. But actually, ClojureScript is already ready, right? Persistent data structures are already lock-free. So if we ever had shared memory parallelism, ClojureScript data structures could be shared between threads, and we wouldn't need locks at all. They already don't require locks. Okay, so hopefully you're excited about trees. Maybe you thought you knew something about trees, and maybe I showed that there are more things to know about trees. But what does this mean for interactive computing? So I'm going to demo a library that I built as an experiment 5 months ago. I was like, wow, I knew persistent data structures were cool, but I didn't really see how they could be sort of aligned with user interfaces. But fortunately, Facebook came up with this really amazing library called React. And once I understood how React worked, I saw that there was a huge opportunity for persistent data structures and building UIs. So the reason React is cool, if you're not familiar with it, React presents on the surface an object-oriented interface. It appears object-oriented. But under the hood, it's actually designed more or less by functional programmers. What it does is says, instead of, you take your app state, your application state, you hand it to React and you say, generate me the virtual DOM. And so React is actually quite functional. You give it your application state and it produces a value, a virtual representation of the DOM. And why this is cool is, say I update my application state, and now let's imagine this is the functional world. I'm not actually changing my application state. I'm just getting a new value. I apply the React function, and it computes a new value, which is the new virtual DOM. And how React actually works is that it diffs those two virtual DOMs, and it produces a minimal change set, which it will actually commit to the DOM. So if you're familiar with graphics programming, this sort of level of indirection should not be so unfamiliar to you. What's interesting about this slide is what happens if I flip the virtual DOM, the two virtual DOMs, if I flip v1 and v0. You're going to get the reverse change set for free, right? React just gives that to you, right? It just gives it to you. So we saw that there's a function from data to UI, right? Given that, time travel, undo, rollback, producing deltas, all these crazy things that you think, oh, that's going to take us months to do, right? Just fall out of persistent data structures and React. So I'm going to demo this right now. So I actually showed, I did a version of to do MVC, which is sort of like the standard thing you do with MVC. It's stupid. It's not really realistic, but it's what everybody does. And I did a version of it, and I said, I think I can, with Ohm and React, add undo to this program, maybe 10 lines of code. Turns out it took 5 lines of code, and it was non-invasive. I could add undo to 2MVC, and it took me 5 lines of code. So Jack Shadler, who is a developer at Ableton, was like, that sounds cool, but does that really scale? I mean, does that work with a less trivial application? And so he took that challenge and said, I'm going to build a pixel editor, and it's going to be a 64 by 64 pixel editor. I'm going to represent the image as a bitmap vector tree, right? It's going to have 4,096 pixel values in it. And will any of the things that David says actually work? Will undo be easy, redo, etc.? So I want to demo that for you now. So here we go. You've probably seen pixel editors, but you probably haven't seen ones quite like this. So on the right, you've got a history thing happening. That's cool. But I can click undo. I can click redo. But then I can even scrub. So on the right, I can scrub, and you can see it's not slow. I can scrub here, and it's all persistent data structure underneath. I can start, going like this. I mean, you can do this until you get bored. I've had hundreds and hundreds and hundreds of levels of undo. It doesn't slow down. Doesn't become unresponsive. Right? That's pretty cool. And then you're probably asking, well, OK, how much code did that take? This is all the code. This is all his undo logic. It's all the redo logic. It's all the logic for extracting every frame and converting it into an animated GIF. This is 60 lines of code. There's lots of white space, and most of the functions are 3 lines. Right? So if you've ever done undo before, I don't care what. It's almost always like you give up. It's too complicated, lots of bugs. Right? So this is completely falls out of persistent data structures and the fact that React lets us move forwards and backwards in time. So what you traditionally thought as complex was just because you wanted to build your system with stateful objects. And by removing that, suddenly what seemed like it was difficult is not difficult. OK. And so you're probably wondering, if you care about performance, you're probably like, well, what's the memory usage of something like this? I mean, because if you've done copy on write, it sounds very expensive. So I did a little memory test using the Google Chrome heap profiler, a heap snapshot. And so on the right, what I did was I said, if I'm going to represent in a mutable like with mutable arrays, and if I'm going to save 100 frames, I have to basically copy an array of 4,096 elements containing strings 100 times. That takes 1.7 megabytes. On the right is a persistent vector where I randomly update some pixel and I snapshot it 100 times. It takes 0.2 of a megabyte. It uses almost an order of magnitude less memory. So hopefully I got you excited about this stuff. This is actually available to JavaScript users. For 2 years, I've maintained a library called Mori. And what it is that, so in the Clojure world, we just use ClojureScript because we like Clojure and ClojureScript. But 2 years ago, I was like, there isn't a good persistent data structure library out there for JavaScript. And ours is the best that we know. It's highly optimized for all the engines. We've spent years working on it. Rich Hickey spent even longer working on it for the JVM. The likelihood that anybody was going to come up with something better was quite low. So I said, we're just going to provide this to JavaScript users. So if you want to play around with React and immutability, you can try Mori. Mori basically exports all the ClojureScript data structures to regular JavaScript consumers. So you can, all the data structures I've been talking about and way more. We have sorted maps, sorted sets, real persistent hash maps, on and on. So yeah, mess around with that if you like. And that's about all I had today, and I can take some questions. Work. Any questions? No?
I got one. I took a look at Mori a while back, but I couldn't find any support for transients. They just don't look hard enough.
So probably a long time ago, or maybe a year ago, it didn't have it. So we have a new namespace called, I think it's called Mutable? Yeah, it's like Mori.mutable, and you have these functions called freeze and thaw. Yeah. Or, right?
Are there any other use cases where you can effectively use the undo operation? Like, I'm trying to think how you would use it in a real world.
Oh, yeah, so that's a good question. I tried to allude to that, but I probably didn't spend enough time on it. So the question was, are there use cases outside of undo and redo? And actually, there's a lot. So you have this huge problem with JavaScript client-side applications where it's like, what happens when, for example, the type of code I hate writing. So I have to present to the user a modal view or some modal state. And you have to be able to exit the modal state. Well, what do you have to do by hand? You construct the modal state, and then when the user hits cancel, you have to reconstruct the previous state. So you don't have to do this anymore in this model, right? You just like, screw it, just go back to where we were. So that's like a simple, common, extremely common UI pattern, modals. So you don't have to write any logic to recover the old state. Also for things like optimistic update. So often you will, because of network latency, you'll be like, we're going to pretend it works just because 99% of the time it does, but what if it fails? So what you do is you often optimistically update the UI, but when it fails, you need to roll back. And again, you have this problem where like, oh, we have to do all this logic to recover this state. Again, you can save the state, try the optimistic update. If in that rare chance it fails, you can recover the state of the application. There are other neat things you can do. So persistent data structures are actually really efficient to diff. So they're actually very fast to diff because of the way that they work. So for example, say the user loses network connectivity. You can't reach the server. It times out. And the user wants to keep interacting. So you can actually keep snapshotting. And what you want to do is you can actually say, well, we want to make sure that if the user closes this window, that they can go back to where they were because we couldn't actually commit it. So it's easy to, for example, compute the deltas. You can quickly compute the deltas and write them to local storage. So there's all these like, it's not like, again, I was trying to say, it's not like you're going to build apps you've never built before. It's more like the things that were difficult previously, these hard edge cases, become tractable. Yeah. Again?
In Ohm, one of the things that I haven't had a chance to dig into yet, I understand why it's faster to use persistent data structures to use diffing. Is that used for your models? Are you using the diffing on the models, or are you using the diffing on the actual elements, just as React does the diffing on the JSX elements?
So we don't do diffing on the elements. That's all React. We just do diffing on the model. We mostly use it for the model. Yeah. See, there was a question back there.
So if you look at the React trifecta, we have React, we have RxJS, and we have core async. How do those things fit together? Is RxJS competitive with React, competing with React, and how does core async fit in there?
So it's not competitive at all with React. React just does something completely different. React is about rendering. So things like core async, things like RxJS, those are about coordination. They're actually still really useful when you couple them with React. React is a rendering layer. That's all it's really there to do. Did it? Cool. Well, thank you.